Hello everyone, my name is D. Shravanjati. My roll number is 24BQ180427. Today I give the seminar on the subject of switching theory and logic design. In this subject, I take this topic about flip-flops. In this flip-flops, I was mainly discuss about the types of flip-flops, in types of flip-flops explanation and applications, uses, all this stuff. I give the seminar on this flip-flops topic. First one is the building blocks of digital memory. The building of digital memory are uses of flip-flops. See this explanation. Exploring the fundamental sequential logic devices that power modern computing systems, enabling storage, synchronization, and state management in digital. The building blocks of digital memory are mainly sequential logic devices of mainly used this sequential logic devices and computing systems. Flip-flops are mainly used computing systems enabling storage, synchronization, and state management in digital. Next one is what are flip-flops. In this flip-flops topic, I have mainly discussed about the what are flip-flops. Flip-flops introduction is given there. See this introduction of flip-flops. See this flip-flops circuit diagram. In this way we have to connect the flip-flop circuit diagram. See this flip-flops. What are flip-flops? Flip-flops are digital sequential logic devices. Fundamental to digital electronics, they possess two stable states and remain in one state until triggered by an input signal. Unlike combinational logic that produces outputs based solely on current inputs, flip-flops retain information and from the foundation of memory elements, counters, and state machines in digital systems. I have to explain step by step this flip-flops. Flip-flops are digital sequential logic device fundamental. These flip-flops are digital sequential logic devices. Sequential logic devices are sequential logic devices and combination logic devices. Sequential logic devices are using flip-flops. Next one is they possess two stable states and remain in one state until triggered by an input signals. Flip-flops is mainly used clock triggered. In this way we have to use the flip-flops. See this three bistable states, memory functions, sequential logic. Bistable states, two stable logic levels, high 1 and low 0. Memory function, retain output state between clock pulses. Sequential logic, output depends on past inputs and current state. Next one is types of flip-flops. Types of flip-flops, we have four flip-flops are there. In first one is SR flip-flop, second one is JK flip-flop, third one is T flip-flop, fourth one is D flip-flop. These are the types of flip-flops. See these diagrams. These are the diagrams of types of flip-flops. SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. We have to discuss this step by step. First one is SR flip-flop. SR flip-flop. An SR flip-flop is a fundamental digital circuit used for storing a single bit of information. It has two inputs. First one is set, reset. SR means set, reset. Yes and two complementary outputs, Q and Q bar. SR means two outputs. First one is set, second one is reset. In this way we have set. SR flip-flop diagram. See this SR first two inputs SR. Next one is JK flip-flop. JK flip-flop is a simple 1-bit memory device in digital electronics that can be in one of two states, 0 or 1, and changes its stable based on clock signals and its two impulse, J and K. See this diagram. SR flip-flop and JK flip-flop is small difference. See this difference, we have to connect the Q bar to S input, Q to R input. In this way we have to small change between the SR flip flop and JK flip flop. Third one is T flip flop. A T flip flop is a sequential logic circuit that toggles its output changes from 0 to 1 or 1 to 0 when the clock signal triggers and the toggle input T is set to 1. T means toggle. Toggle are changes 0 to 1 or 1 to 0. See this T flip flop diagram. These diagrams changes only small change, all are same. Next one is D flip flop. A D flip flop is a simple digital circuit that acts as a memory cell storing a signal bit of data. See these diagrams once again. Small difference between these diagrams and all of one same. Next one is understanding the SR flip flop. We have to deeply understanding this SR flip flop, JK flip flop, T flip flop, D flip flop. Understanding the SR flip flop, we have, before we see definitions and circuit diagrams, in this SR flip flop we have to understand the SR flip flop, set, reset and intermediate states. See this operating modes. Set is S is equals to R, S is equals to 1, S is equals to 1, R is equals to 0. Forces Q output to 1. This S is equals to 1, we have forces Q output to 1. Q is becomes output 1. Next one is reset. Reset means S is equals to 0, R is equals to 1. Forces Q output to 0. Q is becomes 0. Hold means S equals to 0, R equals to also 0. Maintains previous state. Next one is interminate. Interminate means S is equals to 1 and also R is equals to also 1. This means interminate. Next one, this means unpredictable output avoided in practices. I hope this understanding is mainly understanding this. See this, the SR flip flop forms the foundation of sequential circuits. Its simplicity makes it ideal for understanding basic flip flop operations. Through the intermediate state limitation led to develop of more sophisticated variants. And see this diagram once. Set, reset, trigger or clock. We have represent any one, trigger or clock. I will take NAND gates. This NAND class represent an OR gate. Also we have to draw this circuit diagram. See this diagram. Next one is D flip flop. The D flip flop data latch of synchronous system. Key characteristics: single data input, eliminate indeterminate state, output equals input on clock pulse, ideal for synchronous systems, core building block of registers. The D flip flop captures data on clock edges, making it essential for registers, shift registers and microprocessor controller. It guarantees that data is reliable, referred and stored at predetermined clock intervals, enabling synchronized digital systems operations. See this diagram once, and truth table also given there. This diagram, D flip flop is only one input. See this carefully. Truth table is also there. Next one is JK flip flop, overcoming indeterminacy. See this, J is equals to 1, K is equals to 1 means hold state, no change to output. Next one is j is equals to 1, k is equals to 0. Set state, q becomes 1 and j is equals to 1, k is equals to j is equals to 0, k is equals to 1. Reset state, q becomes 0, j is equals to 1, k is equals to also 1. Toggle state, these means toggle state, output switches to opposite state. See this truth table and circuit diagram. Clock, CLK means clock, Q bar. The JK flip flop eliminate the indeterminate state problem of SR devices. With both input high, it toggles out, providing greater versatility. This makes it invaluable for counters, frequency divider and complex state machine required flexible control. Next one is T flip-flop, toggle action for frequency division. Operating principles, T is equals to 0, hold current state. T is equals to 0 means hold current state. T is equals to 1 means toggle flip-flop to opposite state. See this diagram, truth table also given there. Next one is primary applications. The flip-flop excels in binary counters and frequency dividers. Each toggle divides frequency by 2, enabling straightforward constructions of counters that divide clock frequency by powers. 2 cascading T flip-flops creates multi-bit binary counters essential to digital systems. Next one is clocked flip-flop synchronizing operations. See this, all of these we have to use clock. Clock are mainly two, negative clock, positive clock. We have mainly used clock or positive clock. Positive clock, negative clock. See this, clock signal synchronized flip-flop operations, ensuring predictable state transitions. Edge triggered flip-flops responding on rising or falling clock edges, while level triggered designs respond during high or low clock reliable. High we have to high represent, we have to know these clock is positive clock, or no low clock we have to represent, we have to know this represent negative clock. In this way we have to understand this clock. This timing synchronization prevents race condition and ensures reliable data transfer across digital systems. See this diagram. First we have take the clock, and next one A0, A1, B1 clock enable A, clock A. In this way we have to take this clock. We have to represent the first high to low, low to high. We have to plot this. In this way we have to all of these A0 this way, plotting A1 this way, B1 this way. We have to all of these we have to plot this one. Next one is edge triggered, level triggered, master slave. We have mainly discussed about this master slave. Master slave, first one, two flip-flops are mainly used this master slave. Master is for example JK, or slave is for example SR. We have taken this edge triggered respond on clock rising or falling edge. Level triggered respond during enter clock high or low. Master slave, two-staged design eliminating timing issues. Next one is applications of flip-flops from registers to counters. Last topic of this flip-flops, we have mainly discussed about these applications of flip-flops. See this applications of flip-flops is mainly we have registers, counters, shift register, state machines. Registers, groups of flip-flops store multi-bit data temporarily essential in CPU architectures for accumulation values and intermediate computations. Next one is counters. Cascade flip-flops count clock pulses, enabling frequency division, timing circuits, and event counting in microcontrollers and industrial systems. Third one is shift registers. Fourth one is state machine. In this way, we have used this applications in our daily life. Next one is key differences and choosing the right flip-flop. Key differences of these flip-flops. Type SR. Inputs are set, reset. Indeterminate S. Toggle no. Best for basic logic. D. Data. Indeterminate no. Toggle no. Best for registers. Type JK. Inputs JK. Indeterminate no. Toggle S. Best for complex controls. Type T. Inputs toggle. Intermittent no. Toggle yes, best for counters. See, this selection depend on application requirements. Use D flip-flops for straightforward data storage and registers. Choose JK or T for counters and frequency division. SR remains useful for understanding fundamental but is rarely used in modern systems due to indeterminacy. Last one is conclusion. Flip-flops in modern digital designs. Foundation of memory. Enable state retention and data storage across systems. Sequential logic. Create complex behavior beyond combinational circuits. Essential building blocks. Underpin registers, counters, and control systems. Continued relevance. Integral to FPGA design and embedded systems. Flip-flops remain fundamental to digital electronics education and practice. Understanding their characteristics, variant, and applications is essential for designing reliable digital systems, from simple counters to sophisticated microprocessor and control circuits. These are we have to mainly use flip-flops. This topic I have discussed in this way. I have to discuss this flip-flop topic. All are thanks.